Hi there, Miss Barber here. Let's do a few examples involving L'Hopital's rule. Begin with example 1. Evaluate the limit as x approaches negative infinity of, in the numerator, the natural log of the quantity x to the 6th plus 2, divided by, in the denominator, 3x. Let's compute the limit. If we let x approach negative infinity for the natural log term, that will end up approaching positive infinity, and in the denominator, 3 times x as x approaches negative infinity will approach negative infinity. This is an indeterminate form that allows us, so we'll write indeterminate, that allows us to use L'Hopital's rule. L'Hopital's rule means that we take the derivative, so let's go ahead and write limit as x approaches negative infinity, the derivative of the numerator and the derivative of the denominator. So let's take the derivative of the natural log of x to the 6th plus 2. That will be 1 divided by x to the 6th plus 2. And then the derivative of the argument x to the 6th plus 2 be 6x to the 5th. And for the denominator, the derivative of 3x is just 3. Let's simplify that. So let's continue to write the limit as x approaches negative infinity. 6x to the 5th divided by 3 simplifies to 2x to the 5th. And the denominator is still x to the 6th plus 2. Now let's divide by the highest degree present. So I'm going to go ahead and write this as the limit as x approaches negative infinity of. We'll divide by x to the 6th, so you'll get 2 over x in the numerator, and the denominator x to the 6th over x to the 6th is 1, and then we still have 2 divided by x to the 6th. Now, let's take the limit as x approaches negative infinity. In the numerator, 2 over x, that'll approach 0. In the denominator, the constant 1 remains, and 2 over x to the 6th as x approaches negative infinity is 0. And so this is 0 over 1, and we get that the limit as x approaches negative infinity of the natural log of x to the 6th plus 2 divided by 3x is 0. Example 2. Evaluate the limit as x approaches 0 of, in the numerator, 1 minus cosine x, divided by, in the denominator, x plus x squared. Let's take the limit. We will have 1 minus cosine of 0 is 1, divided by, then we will have 0 plus 0 squared, which gives us 0 over 0. It's indeterminate. And that form allows us to use L'Hopital's rule. So because of that, we can apply L'Hopital's rule, which tells us that we can take the limit as x goes to infinity of, and we take the derivative of the numerator divided by the derivative of the denominator, and it gives us the same limit as before we took it. So we will have the derivative of 1 is 0, the derivative of cosine x is minus sine x, so minus sine x would be positive sine x, and in the denominator the derivative of x is 1. And the derivative of x squared is 2x. So now, let's see what happens if we evaluate. We will get sine of 0 divided by 1 plus 2 times 0. Sine of 0 is 0, and that's divided by 1, so the limit is 0. Example. Evaluate the limit as x approaches infinity of x times the tangent of 1 divided by x. So let's see what happens. As x goes to infinity, we will have x times, and then the tangent of 1 over x approaching infinity, would be 1 over infinity, which is 0. Tangent of 0 is 0. This is an indeterminate type, but we have to manipulate it so that we either get 0 over 0 or infinity over infinity. So let's manipulate, algebraically manipulate. So we will have the limit as x approaches infinity of tangent of 1 over x. And we can write x as 1 over x, which is equivalent. Now, when we take the limit as x approaches infinity, we will get 0 over 0. This form allows us to use L'Hopital's rule. So now we can use L'Hopital's rule. That means we're going to take the derivative of the numerator and derivative of the denominator and then take the limit. So the derivative of tangent is going to be secant squared. Then we need to take the derivative of 1 over x, which is minus 1 over x squared. And in the denominator, the derivative of 1 over x is negative 1 over x squared. Now, algebraically, the negative 1 over x squareds cancel, so we can simplify this as limit as x goes to infinity of, and now we have just secant squared of 1 over x. Now we can take the limit. As x approaches infinity, the 1 over infinity approaches 0, so we're looking at secant squared of 0, and that is 1. Example 4. Evaluate the limit as x approaches pi over 2 from the left of tangent of x raised to the power of 2x minus pi. When we take the limit and let x approach pi over 2 from the left, for the tangent x portion, that approaches infinity, and in the power, the exponent, you're going to get 2 times pi over 2 minus pi, which is 0. That tells us we need to do something else to get it into an indeterminate form with which we can work. When you have stuff in the exponent, as a general rule, you're always going to use natural log. So let's observe that tangent, we're doing a little bit of backtrack, x to the power of 2x minus pi is equal to e to the natural log of tangent of x to the power of 2x minus pi. The natural log or logarithms have nice properties that lets us write the powers as coefficients. So let's see what I'm going to do with this. Okay? What we're going to do is then say that the limit as x approaches pi over 2 from the left of the original form, tangent x to the 2x minus pi gives us the exact same limit as if we did e raised to the power of the limit as x approaches pi over 2 from the left of the natural log of the tangent of x to the power of 2x minus pi. We are going to deal with the power portion and then we'll raise it to the e value when we're ready. So we'll start with here and we're going to look at the limit as x approaches pi over 2 from the left of the natural log of the tangent of x raised to the power of 2x minus pi. Let's write it so that the exponent is a coefficient. So that will be equal to the limit as x approaches pi over 2 from the left of 2x minus pi times the natural log of the tangent of x. We're going to do one more rewriting. So copying from the previous slide, the limit as x approaches pi over 2 from the left of, we had 2x minus pi times the natural log of the tangent of x. Let's rewrite this so that we have it as the limit as x approaches pi over 2 from the left of the natural log of tangent of x divided by 2x minus pi to the negative 1. So we write it as a reciprocal, and when we do, we get that much coveted infinity over negative infinity. And this tells us we can now apply L'Hopital's rule. So let's do that. We're going to apply L'Hopital's, okay, because we got the form we needed. And we will have the limit as x approaches pi over 2 from the left, taking the derivative of the natural log of the tangent x, which would be 1 over tangent x, times the derivative of tangent x, which is secant squared x. And then in the denominator we will have, using the chain rule, negative 1, 2x minus pi to the negative 2, and then the derivative of the inside function would be times 2. Let's clean this up a little bit more. Without changing any values, I'm going to reorganize some of these components. So I will write this expression as the limit as x approaches pi over 2 from the left of, and I'm going to write the minus 1/2 2x minus pi squared in one position, and then put the trig stuff together. So I will have 1 over tangent x times secant squared x. That makes simplifying a little bit easier. Continuing, let's factor out the constant 1/2. So we have minus 1/2 times the limit as x approaches pi over 2 from the left. And we still have the 2x minus pi squared. Let's do a little bit of trig to clean it up. Let's simplify the 1 over tangent x times secant squared x. And I'll do that by changing everything to sine and cosine. So 1 over tangent x I can re-express as cosine x divided by sine x. And secant squared x I can re-express as 1 over cosine squared x. Now when that simplifies, we end up with 1 over sine x cosine x. Let's write that into our limit portion. So replacing the 1 over tan x secant squared x with its equivalent sine and cosine, we'll write 1 over sine x cosine x. Let's see what happens here when we take the limit. I'm going to clean it up again. Negative 1/2. The limit as x approaches pi over 2 from the left, 2x minus pi squared divided by sine x times cosine x. Well, let's see. We go to pi over 2 from the left, 0, and sine x cosine x as x approaches pi over 2 from the left is 0 over 0. With the 0 over 0, let's do L'Hopital's rule. That means we're going to take the derivative of the numerator and the derivative of the denominator, which will give us negative 1/2. The limit as x approaches pi over 2 from the left, the derivative of the numerator using the chain rule, bring down the 2. So 2 times 2x minus pi raised to the power of 1. And of course the derivative of the inside is going to give me 2. And then on the bottom we will do the derivative of the first, so cosine x, and then the second function, and we will have plus, taking the derivative we'll have sine x, and the derivative of cosine is minus sine x. Let's clean that up some more. So we've got negative 1/2, the limit as x approaches pi over 2 from the left of, and we get 4. 2x minus pi divided by cosine squared x minus sine squared x, and we can actually take the limit. This is going to be, so let's not forget the 1/2, and if you have pi over 2, 2 times pi over 2, that's going to give you the pi. Pi minus pi is 0, so you got 0 over, and then for cosine squared, we're going to have 0 minus 1 squared. And so that's going to be equal to negative 1/2 times 0, which is 0. Almost done. But remember, way back when we started this problem, we said that the answer is e raised to the limit of whatever this expression turned out to be. So pi of the natural log of, let's go ahead and write it out, tan x divided by 2x minus pi to the negative 1. So that's actually e raised to the 0, and the limit is 1.